So proceeding on to the first question, P and S are 2 points on a gravitational equipotential surface, right? So that means the potential of the point P is equal to the potential of the point S, okay? Q and R are 2 points on a different gravitational equipotential surface. So that means the potential of the point Q is equal to the potential of the point R, right? So the greatest work done by the gravitational force is when moving a mass from P to S, okay? So explore option number A. So what is the work done in transporting a mass from the point P to the point S? This is equal to mass into potential of the point P minus potential of the point S. Okay, so from here we know that the potential of the point P is equal to the potential of the point S, so it's equal to 0. Okay, now exploring the second option. Okay, from Q to R. Okay, so so the work done will be equal to m times of potential of the point Q minus a potential of the point R. Again see, the potential of the point Q is equal to the potential of the point R. Okay, so that means again the work done over here will be 0. Okay, now coming to option number C, the from R to P. Okay, so that means the work done in transporting from R to P will be equal to m times of potential of the point R minus potential of the point P. Okay, now what is potential at point R? This is equal to minus of G capital M divided by your small r, R of capital R, right? Now what is capital M? Capital M is the mass of the planet, okay, and small m you know is the mass you want to move. Okay, now what is the potential of the point P? Potential of the point P is again minus of G capital M divided by radius of the point P, so R of P. Okay, so this is R of R, radius of the point R, and this is R of P, radius of the point P. Okay, now as you know from the diagram, R is at a capital R is at a greater distance than capital P. So that means R of capital R is greater than R of capital P. So that means 1 by R of capital R is less than 1 by R of P, capital P. So that means 1 by capital R minus 1 by R of P should be less than 0. Okay, so this relation we know. So now put this, so work done will be equal to m times of, what is VR? VR is minus of G capital M divided by R of capital R, right? Minus what is potential of the point P? Potential of the point P is again minus of G capital M divided by R of P. Okay, so from here we get that M, I take common everything, 1 by R of P minus of 1 by R of capital R. Okay, so see, this term was less than 0, so that means if I multiply with minus 1, R of P minus 1 by R of capital R is greater than 0, right? So that means this term is greater than 0. G is always greater than the 0, M is always greater than 0, small m is always greater than 0. So that means the work done is greater than 0. Okay, so that means the correct option to this question is option number C. Similarly, you can find out option number D, the work done, it will come out to be less than 0. Okay, leave it as a homework to you. So the question, so the correct option is option number C. Okay. Now proceeding on to the next question, the graph shows the variation of electric field strength E with distance R from a point charge. Okay, the shaded area X is the area under the graph between two separations R1 and R2 from the charge. So what we have to find out, what is X? So over here X is what? X is the area under ER graph, area under your electric field strength and radius R, okay, graph, okay, which is nothing but, we have taught that this is nothing but the potential difference. Okay, area under the ER graph represents the potential difference between the 2 points. So this will be equal to your V2 minus of V1. Okay, so this is the nothing but the potential difference between the points R1 and R2. So this is the correct option. The option number B is the correct option. Now proceeding on to the next question, why are high voltages and low currents used when electricity is transmitted over long distances? High voltages are used in order to minimize the power lost when transmitting electricity over long distances. Okay, and why are low currents used? So suppose there is a wire. Okay, in this wire the electricity is being carried over long distance. Okay, so this wire will have some resistance also, R. Okay, and what is the heat produced in this wire of resistance, R? I square RT, right? Now, so the heat is actually proportional to the square of the current, right? So that means low current, when there will be low current, there will be low amount of heat that is produced. That means the lower the energy is being lost. And if there is high current that is flowing through the wire, the heat that will be generated will be much higher. So that means the energy will be lost higher, right? So what do we want? We want the minimum loss of energy, right? So that means we have to keep the I, that is the current, low in the wire. Okay, so that means the correct option is option number C. Energy losses are reduced both by keeping the high voltage and by keeping low current in the wire. So proceeding on to the next question, the power P is dissipated in a resistor of resistance R when there is a direct current I in the resistor. Okay, so what is the power P? Power P is equal to I into R square, right, for direct current. What is the average power dissipation in a resistance R by 2 when alternating root mean square RMS current is 2I? Okay, so that means P would be equal to your now VRMS into IRMS. For AC currents we know this. Okay, so that means P can be also written as, now VRMS can be written as resistance into IRMS, so into your IRMS. Okay, so now what is the resistance? The resistance is R by 2, right? So that means the resistance is R by 2. IRMS is what? IRMS is given in the question to be 2I, right? So this is 2I into 2I. Okay, so that means the power that is produced, so this is equal to your I square R 2I square R. Okay, so what is I square R? This is P. So that means the power that is produced, P dash, the power that is produced, P dash, is equal to your twice of P. Okay, so that means the correct option to the question number 34 is option number B. So proceeding on to the next question, that is your question number 35. A rectangular coil rotates at a constant angular velocity. At the instant shown, the plane of the coil is at right angles to the line ZZ. Okay, a magnetic field acts in the direction of ZZ, right? So that means the magnetic field is acting in this direction. Okay, in the direction of ZZ. Okay, okay. So see that the total graph, if it would have been rotating, would be this, right, the sinusoidal graph, but the graph is up till 1/4 of that, right? 1/4 of the total graph. The total graph was produced on rotating it by 2 pi, right? The graph that is produced by rotating it by 1/4 of this will be equal to pi by 2. That means it has been rotated by an angle of pi by 2. So we can rule out this one and this one. Okay, now along which axis this is rotated, now that is the question. Okay, so if you rotate this by the ZZ axis, okay, so what will happen if you rotate this along the ZZ axis? It will rotate somewhat over in this direction, right? Induced EMF E is equal to your NBA sin phi, where phi is the angle between the area vector and the magnetic field. Okay, so when it is rotated by the ZZ axis, what happens? It's rotated in this manner, right? Initially, what is the angle between the area vector and the magnetic field? See, the area vector always points outwards and the magnetic field is also in the ZZ direction, right? So that means initial area is 0, initial angle is 0 degree. Okay, now when it is rotated, so that means after some point, just let me rub this, after some point, so after some time this will be rotated like this along the ZZ plane. Okay, so after some time the area vector will be same in the ZZ plane, in the ZZ direction. Okay, why? Because area vector always points outwards and magnetic field is also the same in the ZZ direction. So that means the final angle is also 0 degree. So that means the change in the EMF is also 0 degree. Why? Because sine 0 is 0. You can put this and you can see. So option A is incorrect. Okay, the option that remains is option C. So option C is the correct option. So the answer to question number 35 is your option C. Now proceeding on to the next question. A capacitor of capacitance C has an initial charge Q. The capacitor is discharged through a resistor capital R. Okay, the potential difference V across the capacitor varies with time. What is true for the capacitor? After a time RC by 2, the potential difference across the capacitor is halved. Okay, so we know the potential difference across the capacitor V is equal to the initial potential difference across the capacitor, right, which is V naught e to the power minus of T by RC. Okay, so now after the time RC by 2, okay, so that means after the time RC by 2, the potential difference across the capacitor will be V naught minus this, right? So that means this will be equal to your V naught by root E, right? So that means the potential difference will not be halved, right? Instead, the potential difference is changing by a factor of 1 by root E. Okay, so that means option number A is incorrect. Now proceeding to option number B. The capacitor discharges more quickly when the resistance is changed to 2R. Okay, so when the resistance is changed to 2R, initial time constant was RC. Now the time constant is 2RC, right? So we know that when the time constant increases, the capacitor discharges less quickly. Okay, so we know that when the time constant increases, the capacitor discharges less quickly. So that means the capacitor takes a while to discharge. Okay, so that means the option number B, that the capacitor discharges more quickly, this is also wrong. Okay, so proceeding to option number C, the rate of change of charge on the capacitor is proportional to V. Okay, so the rate of change of charge on the capacitor, the dq by dt, is equal to the current I that is flowing in the circuit at that particular moment, right? And I is, we know that I is proportional to V, right? So that means the option number C is correct. Okay, now proceeding to option number D, the time for the capacitor to lose half of its charge. Okay, so we know that the charge on the capacitor Q varies as Q equal to Q naught e to the power minus of T by RC, right? So the time for the capacitor to lose half of its charge, then that means the final charge that will remain is Q naught by 2. Okay, so Q naught e to the power minus T by RC. From here we can find out the T, right? So from here we get that half is equal to e to the power minus T by RC. So from here we get that ln of half, this is equal to minus of T by RC, right? So over here we get that minus ln 2, this is equal to your minus of T by RC. This and this get cut. So that means the time after which the charge on the capacitor gets half is RC ln2, not ln2 by RC. So this is also incorrect. So this is also incorrect. Okay, now proceeding on to the next question. Monochromatic light is incident on a metal surface and electrons are released. The intensity of the incident light is increased. So when the intensity of the incident light is increased, what happens? The rate of the emission of electrons, increases. Okay, so the rate of emission of electrons increases. So this is a fact, you have to remember this. Okay, increases. Okay, so that means which of the following option within A or D will be the correct option. Okay, so now they are also asking about the kinetic energy of the emitted electrons. Okay, so while increasing the intensity of the incident light, the kinetic energy of the emitted electrons does not increase. Why? Because we are not increasing the energy of the incident light, we are just increasing the intensity of the incident light. So that means the kinetic energy of the emitted electrons will be of no change. So that means the correct option to this question is option number D, that is increase and no change. So proceeding on to the next question, the diameter of the nucleus of a particular nuclide X is 12 femtometer. Okay, so that means the diameter is given to be how much? 12 femtometer. So that means the radius, okay, this is diameter divided by 2, so this is equal to your 6 femtometer. Okay, now what is the nuclear number of X? Okay, so we know that R is equal to R naught a to the power 1 by 3, right, where a is the nuclear number. Okay, so what is R is 6. Now what is R naught is 1.2 femtometer. Okay, so a to the power 1 by 3. Okay, so that means 5 becomes equal to a to the power 1 by 3, or a becomes 5 cube, so this is equal to your 125. So this is the correct option. The correct option is option number C, 125. So proceeding on to the next question, the photon has a wavelength lambda. What are the energy and momentum of the photon? Okay, so we know that energy is equal to your h nu, where nu is the frequency of the photon. Okay, and nu can be written as c by lambda. So energy becomes hc by lambda. Okay, again energy can be written as p into c, where p is the momentum and c is the speed of light. Okay, so that means over from here I can write that momentum p is equal to your e by c. Okay, and what we derived, e as hc by lambda, so hc by lambda divided by c. So over here momentum comes out to be h by lambda, so that means the energy is hc by lambda and momentum is h by lambda, which corresponds to option number A. So question number 39, option number A is the correct option. Now proceeding on to the question number 40, the Rutherford-Geiger-Marsden equation shows that I can right off the back say you that the correct option to this question is option number C. Why? Because we know that a large portion of alpha particles in that experiment was undeflected. Okay, and this was the main theme of the result of the experiment also, that the large portion of the alpha particles were undeflected, are undeflected. Okay, so that means the correct option to this question, that is question number 40, is option number C.